Races. Welcome everybody. Hopefully you can see me. My internet's not doing the greatest today. We're going to start on to our second lesson on derivatives. Today we're finishing off limits, and we're going to go into the stuff with derivatives, which is basically slopes. It just is about slope. So welcome, Hamza. Nice to see you. I want to finish off limits, and the very first thing we're going to do is to discuss the limit as x goes to 0. So yesterday what we did is we talked about the limits as we reach a certain x value. So what that means is, for example, if we had a function, could be any function, maybe, I don't really need to draw a picture. You just choose an x value and tell me what happens as we come closer and closer from the right side, closer and closer from the left side, and tell me if the y value you're trying to get to is the same on both sides. And for your standard numbers, that's pretty common. The problem is sometimes we divide by 0. And we talked about that yesterday. We divided by 0 a few times. But today we're going to divide by 0 in a little bit of a different way. And what I mean by that is just consider this case, the limit as x goes to 0 of 1 over x. All right, what happens when we go closer and closer to 0 for this number? So what I like to think about is if you're going close to 0, let's say from the right side. If you're going closer and closer to 0 from the right side, it's actually going to explode to infinity. And how I know that is because what we're really doing, as we get closer and closer from the right, we're going like, let's say we have the value 0. We're going like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We're right next to x. But we get even smaller, like a half, and a half again, and a half again. So we're dividing by this like tiny, tiny, tiny small positive number. And if you divide by a tiny, tiny, tiny small positive number, imagine a tiny number like 0.000000001. You can even put it in on your calculator. 1 divided by the smallest number you can make on your calculator. What it's going to do is it's going to explode. It's going to be a massive number. And that gives you positive infinity. And the graph confirms that. If we do the same thing from the left, let me just quickly write it down. If we talk about what happens to dividing by 0 when we come by the left side, really what we're doing, if you follow what I said, it should be simple. We're still dividing by a small number, but we're dividing by a small negative number, which you can imagine to be like negative 0.0000000000001. The smallest number you can think of, the smallest number you can make on a calculator. And if you do that, you can even type that into your calculator, see what you get. I'm going to do it. 1 divided by 0.0000001. I get like 1 with a whole bunch of zeros after it, which is going to get bigger and bigger. So it's going up to infinity. So say it's negative infinity. So that's our intellectual version. Let me show you what it does on a graph. It's a little bit easier to understand by the graph. Let's look at the graph here. This is the graph of 1 over x, okay? This is the graph of 1 over x. Very simple to see this one. The limit as x approaches 0 from the left. So we're approaching 0. What happens? It explodes up to infinity. Sorry, sometimes my pen doesn't work the way I want it to. As we go closer and closer to 0, it shoots up. It goes to positive infinity. We covered this yesterday, actually. As we go from the left side, it shoots down to negative infinity. So the math works. If you punch it into a calculator, that works. You can also see it by the graph. And the way we're going to consider this is these two things. Look, the limit from the left, let me make this smaller. The limit as x approaches 0 from the left is negative infinity. The limit as x approaches 0 from the right is positive infinity. So what it means is the limit doesn't exist. So we'll write down this. Does not exist, and we can move on. All right? I guess I should have added 1 over x. Does not exist. We did that yesterday. What about if we have a slightly different function? So let me just do it on Desmos. What if we had the function 1 over x squared? Well, it looks like this. We covered this yesterday. You tell me, what happens as we go towards 0 for this function? What is clearly happening with this graph? As we come from the right side and as we come from the left side. What are the y values doing? They're going up, 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 up. They're going up into space. They're going to positive infinity. So we can just say that. The limit as x approaches 0 of 1 over x squared, it goes to infinity from the left side and from the right side. So that's our limit. The reason I just brought up Desmos was when we have functions that are going towards 0, we can actually use Desmos to figure it out if you want. There's nothing wrong with that. So let me show you some examples. It says the limit as x approaches 0 of x to the power 1 over x to the power of any number is infinity or negative infinity depending on the power of n. Let me just very quickly show you some examples. A, this function, if you believe me, looks like this. Okay, it goes up like this. I won't draw the arrows because I don't want to confuse you too much. It looks like that, so limit as x approaches 0 is infinity. Done. If you have a x equals 0 or x towards 0 form, you can graph it if you want. I'm giving you permission to use Desmos. That's all you need to do. What's the answer for this one? Well, the graph for this one actually looks like this. It goes down and up. So the first one was positive infinity. I should have actually put the plus. For B, notice as we go towards x equals 0, we get two different stories. One saying up, one saying down. So it doesn't exist. Yeah, so Ibrahim, when you say solve one, I mean, I am solving these. When we have an x equals 0, x approaches 0 form, all you need to do is consider the graph. Yeah, when you have, this is a good time to give you a little review actually. So when we're dealing with limits, and this is just like a short cheat sheet for now, if you have the limit as x approaches some number, you're going to have a couple options. The first thing you should do is try direct substitution. Try to put it in. Just 1 second, Mohammed. I'll cover that. Direct substitution. If that doesn't work, try factoring. And then you can cancel things out, okay? And sometimes there's another strategy you can use. If you have a limit as x approaches 0, now 0 is of course a number, but it's a special number that comes up a lot in a different way. You can't generally do direct substitution. You know, I'm pretty much giving you the opportunity to use Desmos here. It's easier just to look at the graph. You could do it without looking at the graph, but it's much easier to use the graph. And then by the end of the day, in a few minutes actually, we're going to consider what happens when it goes to infinity. And we'll consider that as we get to it. So I think, Mohammed, are you saying it's infinite because you looked at the answer key? Because I looked at the full solutions that Mr. Tom had made for this, and this is one rare case where he made a mistake. Okay, well, oh, he didn't make a mistake. You're right. You're right. That's not what this looks like. What it looks like is it canceled out. So I was the one who made a mistake. It's 5 over 2x squared. That actually looks like this. So you're right, it is infinite. My bad. My bad. You can also think of it this way. This will be 5 over 2 times some tiny, 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 tiny positive number. And square that. Well, that's going to be infinite. Okay. Let's move on to the next one. Thanks for that, Mohammed. The next one. This one does look like this. That's my bad. Sorry about that. And then that doesn't exist. As I can see, just by looking at it, it doesn't exist. And then the fourth one looks a little bit weird. but it's no more difficult. It just looks like this. So if we graph that, what does that do when it's going to x equals 0? Well, it's going to infinity, but actually negative infinity. So we say it goes down forever. The y values are going bigger and bigger and bigger in the negative direction. So we say negative infinity. So just make sure that you have that negative there. So you might notice there is a pattern here. Maybe you noticed it, maybe you didn't, but I'm going to show you something. Let me show you on Desmos. I want you to take care to look at what the answers are here. Or sorry, what the functions are. Okay, Abdo, I just sketched the graphs for you, but you would just pop in the graphs on Desmos, like on a graphing calculator, or you could bring this up on your phone, and you just type the graph in. I knew what the graphs looked like, but let me give you a shortcut first, so you don't need to worry too much, okay? Let me just give you a shortcut. If you have any number, really, with an x on bottom, so this could be like 2 over 7x, or it could be 7 over 5x. It really doesn't matter. The fact is there's an x on bottom. It's always going to look like this, okay? So 1 over plus or minus anything with x looks like this. If you have a squared on bottom, it looks like this. In fact, any even number looks like that. So what I'm trying to say is that if you have 1 over x to the power of an odd number, it'll look like this. If you have 1 over x to the power of an even number, it'll look like this. All right, so the limits, these limits, I'll show you. If you have 1 over x to the power of an odd, the limit does not exist. If you have 1 over x to the power of an even, the limit does exist. It's either positive or negative. I'm going to show you something. If it's a positive number, it'll be positive infinity. If it's a negative number, it'll be negative infinity. All right, but really it's much easier just to graph it and see. So let me show you one more time what they all look like. 1 over x looks like this, limit doesn't exist. 1 over x squared looks like this, limit does exist. So you're saying if the power of x is down is odd, doesn't exist. Exactly. So look at this. I'm going to turn on all my odd versions. You see how all of them, those limits don't exist because they don't agree. And I could keep going every single possible combination of odds. And then my evens, if it's even on bottom, it will exist. It'll be positive infinity. If it was negative, maybe if this was negative 1, I'll bring up the keyboard again. Negative 1. Sorry, guys. Minus 1. It would be negative like this. But that's what I just said. So I'll repeat myself in the notes. It's a shortcut. You can use Desmos as a shortcut, or you can use this shortcut. If you have a positive plus or minus number over x to the power of an even, you'll get plus or minus infinity. Plus, plus, negative, negative. So your evens, it'll give infinity. You just need to be careful about the sign. If you have anything, any plus or minus over x to the power of any odd, once you simplify, of course, it's going to give us does not exist. Good afternoon, Mohammed. Okay, how do we feel about that? Can I move on? I'd like to move on. Bob, though, you've got it. What about the rest of you? Okay. If you don't understand, try to go back and listen to my wise words again on YouTube or so on. Don't graph for you. You'll only get better at something by seeing it more and practicing. But that's why I try to give you more than one way to do it. Okay? It's a weird concept. I get that. Absolutely. Let's do one more case, the last case, the limit as x goes to infinity. Why does my computer do this to me? The limit as x goes to infinity. So what happens as we get further and further to the right and further to the left? And let me just go ahead and show you a quick example here. It says 1 over x. What happens when x gets bigger, 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 bigger? So really what we have 1 over a number on bottom that's getting bigger and bigger and bigger. So we have this giant positive number. What's 1 divided by some giant positive number? Now this is a positive number here. If you take one thing and divide it into a million tiny little pieces, every piece is going to be small, right? For example, you could, on your calculator, type in 999999999999999. What's 1 divided by 99999999999? It's essentially 0. It's getting closer and closer to 0, certainly. So 0. The limit, let me just, spoiler alert, the limit as x approaches infinity of anything with x on bottom like that, it's going to be 0. It goes to 0. Let's do the same thing with x squared. With x squared over here on the right, it's still 1 over some big number, some big positive number. We're just squaring it. So it's even more 0-ish. So it's still 0, right? If you divide it by 10, look what happens. If you were dividing by 10 squared, you get this answer. If you put in 100 for x, you get this answer. You can notice, hopefully, when you're looking at this, it'll get closer and closer to 0. We're cutting it smaller and smaller until it becomes 0. So this result is very simple. The limit as x approaches infinity of 1 over any power of x is 0. Halas, that's all. Even if it was negative infinity. So it says, there's a little question here. How would the above result be different? Sorry, I'm looking at this. How would the above result be different if x was negative infinity? I'll just say same. It doesn't matter if it's plus or minus infinity. You divide something by, for example, if you divide 1 by a big negative number, you're not going to have negative 0. You're just going to get 0. So no matter what, it still gives that. And then, does it make sense to consider left and right limits at infinity? I'm not even going to explain that, but I'm just going to say no. There's no such thing as left and right limits of infinity because we don't even know what that number is. So that's a challenge question. Don't really worry too much about that. Let's do some math. Let's do the math part of this, and you'll see that this is actually, of all the limit topics, this one might be the easiest because as soon as you see an x on bottom somewhere, it's just going to delete the term. So let's look at this. Very, very important that I talk through this and make the change that I made. It says, listen, to evaluate limits as x goes to infinity, where there are x terms in both the numerator and the denominator, so on top and bottom, start by dividing both the numerator and the denominator by the highest power of x that appears in the denominator. Let me show you what this means. A little example. For example, if we had this. This would be a case where we have x in the top and the bottom. Look what we need to do. It says we need to divide the numerator and the denominator by the highest power of x that we see. Okay, what's the highest power of x that we see on bottom? If you look at the bottom, yeah, there's a 4. The highest power of x is 4. So we divide everything. We divide everything, every single term, by x to the power of 4. So it's a two-step process. Look in the bottom and see what the highest power of x is. Then divide. So we just change its form. What's x squared divided by 4? I'll do this once. So let me make a little note. X squared divided by x to the power 4 is 1 over x squared. This might look like a lot of work, but it's honestly, it's not going to be difficult. It's the same way every time. 3 divided by x to the power 4 is well, exactly like it sounds. What's x to the power 4 divided by x to the power 4? Well, it's divided by itself. It gives 1. And what's 4x divided by x to the power 4? Well, 4x divided by x to the power 4 is 4 over x to the power 3. If you want to know a quick way to do it, there is a very simple way. It's just a subtraction. You will take 4, for example, on this side, take the bigger power and subtract the smaller one and keep it where it was, okay? That's why it becomes 2. 4 minus 2 equals 2. In this case, 4 minus 1 equals 3. So you see what I'm saying? You just take the power and subtract kind of backwards. You'll get lots of practice with this. Let me show you where I'm going with it. Once we're done, we'll get the limit of this. And you'll see why I taught you how to do this. Example 7. Tom did these, but as I said, I'm going to be doing more and more of it myself just because of the nature of the stuff. So let's look at this. Can we do this directly? Can we do this question by direct substitution? Well, no, we can't, because we would end up, okay, one second. Ibrahim says, sir, we take the highest power in the bottom or in the above from both. In the bottom. So the denominator only, the notes kind of make a mistake here. So you only take it from the bottom. Is that okay? All right. We couldn't do this one. You're close, Ibrahim. I'm glad that you're thinking about it. Sorry, Muhammad. We can't substitute. What would happen? We wouldn't get 0 over 0. We would get infinity over infinity. Because we would get infinity squared plus 1, whatever that means, a giant, impossibly huge number squared, 2 times infinity squared plus 3. Well, that's still infinity squared. Well, it's still infinity over infinity. Think of it this way. If it's a giant number and you square it, it's still a giant number. It's still infinity. It's just a different type of infinity. We still don't know what the number is. Anyway, it's infinity form. So divide by which one? Which term are we going to divide by? We're going to divide by this one. Divide every single term by that. So we keep the limit because we're not doing a limit yet. We're doing simplification that will let us do the limit easier. So don't touch the limit. We haven't done the limit yet. We're dividing every term by x over 2. We should get this. We still have our 4 terms. We just have them in a different form. And like, again, if you're not sure, the x squared, we're dividing by x squared, it gives 1. That's our first one. 1 divided by x squared is exactly what it looks like. 2x squared divided by x squared is still 2. 3 divided by x squared is exactly what it looks like. So Mohammed's exactly right. These terms here, you look at these terms, they've got x on bottom, you've got x goes to infinity, they go to 0, and we're done. So of all the limits, these are actually my favorite because they're always done the same way and they work out really easily. Like terms just get deleted all over the place and life is good, right? That's it. That question is done. So I want to show you one way to divide by this, just in case you want to think of it in a different way. If you're okay with this, you can kind of ignore me. But I want to show you one other way to divide that isn't quite in your head. Yeah, you're right, Hamza, it is. So here, what if we wanted to simplify it in a different way? Some students prefer this way. You still take the term on bottom, but you multiply by everything by this. And then you can see it clearly. Multiply, 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 multiply. But in my opinion, my way that I showed you is better because it's faster, takes much less actual work on the page. Nice. So let's do example B. So Hamza, you're saying you divide it by x to the power of 7. Yes, make sure you don't use the 6, just the x to the power of 7. But yeah, it should give you this. 2 over x to the power of, what's the difference between 7 and 3? There's 4 in the difference. What's the difference between 7 and 1? There's 6 in the difference. I forgot the limit. And then we have 6 plus 9 over x to the power of 6. So you can see how these just disappear. You go to 0. You go to 0. You go to 0. Why do they go to 0? Because of this. The limit, the number on bottom is getting massive. Imagine if that number got really big, it would like delete those terms. And that's what we get. So Mohammed's C is 2. I don't know if I've done C. I just did a few of them. Let me see. I don't think I did C. I think C is infinity. I think C is infinite. I'll do it really quickly. I'll keep that up if you need it. Let's see, divide everything by x. I'm actually, yeah, I'll do it this way. Limit x approaches negative infinity. Divide everything by x. Not x squared. Hamza, don't divide by x squared. You should divide by x only. Because that's the highest power in the bottom. Yes, you can, Mohammed. You noticed you could factor it first. It'll work out exactly the same way. So we've got a problem here. This, when we directly substitute, gives us negative infinity over 1, which is negative infinity. Okay. Although you can factor from the beginning. Same thing that Mohammed just said. Let me write it for you. So this is a weird one. Some students have trouble believing me, but they work out the same. And negative infinity plus 2, imagine, why is it negative infinity? It's because it's like if you had this giant, massive, like, planet, and then you had a tiny little ant on it, or a little animal standing on the planet. You wouldn't see the animal, because the planet is so big that anything around it is essentially ignored. It's so big. So if you have this massive, massive, massive number, you can add 2 to it. It doesn't matter. It's still huge. So it's still infinity. That's a tricky one, okay? Are you okay with that? Is that enough? I'd like to move on to the next topic. D you can do on your own. It's the same strategy every time. You'll work out that the answer is 0. You can try it yourself. Okay, so You're saying, why didn't we switch it with 0? Remember that we're approaching negative infinity here. Is that what you're talking about, or are we missing something? So remember, the beginning of the question is what tells us what we're going to do. In this particular question, we're not substituting in 0, we're substituting in negative infinity. And I deleted all the terms that I could, and then the rest I kept. Clear? Okay. Let's move on. The next topic is different. Most of the next topic is easy, except for the very end. But most of the, I would say all of the difficult part of the next stuff I'm going to show you is more so difficult because of the explanation. The math itself is easy. So students still do well on it, even if they don't understand it. Okay. So the next section is like 2 or 3 pages of practice. You can just do them as you like, you know, and when you're studying for the assignment, the next assignment, or the test. These are all practice. And every single answer, full solutions are all online, okay? They're all on D2L right now as we speak. Let's go ahead and find them. So, you've done slope before. Guaranteed you've done slope. I think if you haven't done it or don't remember it, you'll at least hopefully remember it's quite simple. It's like rise over run, right? So we have to consider the slope of a straight line. What I'll say is the reason we're talking about slope is we're moving into calculus, and calculus is all about slope, like the slope of what's called the tangent line, which we're going to do today. Calculus is built from the idea of a slope, and so let's go for it. This is the start of calculus. And I know you did slope, Abdo, because you did it in physics. So don't lie to me. All right, we want the slope of this line. It's rise over run. Or in other words, it's y2 minus y1 over x2 minus x1. Let's just choose any 2 points. I'm just going to say this point and this point. You can choose any point on the line, any 2 points on the line. I could have chose these 2 points, these 2 points, that point. It doesn't matter. I'm making my life easy and choosing nice, easy points. So what is the value here? This is the point 0, 1. This is 2, 2. And I can do rise over run, or I can do y2 minus y1, all that stuff. Some students still don't understand what rise over run means. It means from the first point to the second point, how far have you gone up? Well, in this case, I've gone up by 1. And from the first point to the second point, left to right, how far have I gone to the right? In this case, I've moved by 2. 1, 2 is my run. 1 is my rise. So no matter what way you slice it, you're going to get 1 over 2. So the slope graphically is very simple. Yeah? I hope you'll agree. You've definitely seen it before. No matter what lies you tell me, you've seen this before. The next part, it says to do slope by the proper formula, and I'll do that. Just notice above here, this is x1 and y1. This is x2 and y2. That's all they are, okay? Let's put them into the formula and solve. We have 2, I'll color code after actually. 2 minus 1 over 2 minus 0. You end up with 1 over 2. Ooh, big surprise. They're the same. Of course they're the same. They're the same line. These are from our second point. These are from our first point. Okay? So it looks to me, Mohammed, did you choose slightly different points? Is that how you got 2 and 4? Yeah, and it's fine. You got the same final answer, which means that you did it correctly. So any 2 points makes no difference. You must have taken this point here, which same slope, up 2 over 4, which is 1 over 2. Yeah, okay. So let's keep moving. You've seen this before, so I don't want to spend too much time on reviewing. What I don't think have seen before is what's called the secant line. And the secant line is just, well, let me rewind. First of all, if you look at this curve, how do you tell someone what the slope of that curve is? Like, you know what slope means, right? There's three sort of cases. When we're dealing with slope, you either have, a positive slope, or you have a zero slope, or you have a negative slope, right? This is like our lines. If we have something that looks like this, it's a positive slope. If it's really, 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 really big, it's really steep, that's a positive slope. If it's really, 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 really small, really negative, it's a low slope. And if it's zero, there's no slope. But look at this curve. This curve has a different slope at different places. Like over here, the slope's here. Over here, the slope's this. Over here, the slope is this. Over here, the slope is this. You see what I mean? So in order to get the slope of a curve, we just have to take 2 points on the line and hope for the best. So I'll just choose 2 points. The secant line, should it be accurate? Well, just use a ruler. I mean, for example, I'll show you. If you choose 2 points here, for example, this one and this one, you should have a ruler or, the side of your phone and just draw the secant line. But the secant line, I don't even know if I'm ever going to get you to draw it. You'll probably just be able to grab it from a graph. Anyway, let's keep it going. We want to get the slope. So the slope is rise over run. So we can say it's, the rise is 2 in this case. And the run, what's the run? It's 1, 2, 3, 4. We've gone 4 over. So the run is 4. And of course, you can take the y values and x values as well. It's all the same, 2 over 4. So just by chance, this is also 1/2. Every slope is not 1/2. It just happened to be a half. It's a coincidence. So don't get any crazy ideas. It's just a coincidence. This is just an example. Really, this should have been called an example. All right? Nothing new so far. There's 2 ways to get the equation. So this is the slope of the secant line. We can find the equation of the secant line, or I should highlight this, equation of the secant line. There's 2 ways. The first way, it's called y-intercept form. There's a better name for it called point slope form. And this form looks like this. I'm not going to use it. I just want to write it down in case you choose to use it sometime. It's harder to use. Slope-intercept form is the one that everyone knows, the one that everyone loves. Y equals mx plus b. Abdel, you said x equals 0. Can you, what are we talking about here when we say x equals 0? To get y, yeah. You can do that. There's actually, there's an easier way. We don't need y, because if we want the equation of a line, all we need are the slope, which is m, and the intercept, which is b. And it turns out we already have slope. It's m, of course. To get b, not so bad. You can see it directly from the graph. So I'm doing this one quick because it's not so important to some of the stuff we're going to do today. But we can see directly. All right, so if you're given the graph, it's easy. If you're not given the graph, it's a little trickier. But this is how we would get the slope of a secant line and get the equation of the secant line. I'm not going to do this one just because we barely cover it in this course and there's no point in wasting the time. Final thing on this page, the secant is also called the average slope of the curve between the 2 x values. So secant has another name called average slope. All right, I'm going to keep going. If you need to interrupt me at any time, you just let me know, okay? I don't take offense to that whatsoever. So this example, sketch and find the slope. Well, the sketch is done. Find the slope of the secant line, also known as find the average slope, between x equals 1 and x equals 2. All right, let's try to pick this apart. We need to figure out the slope between x equals 1 and x equals 2. So let's find those on the graph. This is x equals 1. So it's talking about this point over here. I'm going to go ahead and label it right away. That's the point 1, 3. That's x1, y1. And I'm also going to label this. Wait, that's not it. This. That's x equals 2. And yeah, the point is 0, oops, 2, 0. And just so that everyone's keeping track, it's x2 and y2. Thanks, Mohammed. I just saw yours there. So what are we asked to do? We're trying to find the slope of this line. And just as a slight fix here, for some reason there was a typo. You see this 8? It's not negative, it's actually a positive. It's a typo. It's the problem with whoever made the book. So let's get the slope. Slope is y2 minus y1 over x2 minus x1. y2 is 0. y1 is 3. x2 is 2. x1 is 1. The order matters, so be careful. What we end up with here is negative 3. Yeah? On top, negative 3. On bottom, 1. Negative 3 over 1, negative 3. I can solve it without looking for the graph. What? Why are you so scared of graphs? The graph can give you, go down by 3 over 1, negative 3 over 1. Learn to love the graphs. They're okay. Yeah. I wish that we were, I wish there was a couple things. I wish it wasn't an intersession, and I wish that we were face-to-face, because some of these topics, it would be nice to go back over like the fundamentals of graphing. But anyways, we're here, and we got to do with whatever we've been given. So here we have, this is our function. It's been graphed for us. I'm not going to make you graph these. We do need to get the points from the graph. And yes, I'm assuming, Abdo, you took this x equals 1 and you put it into the formula and you got a y value. Perfectly fine. And I'm assuming you did the same thing for the other one. Perfectly fine. Nothing wrong with it. All right. Now we need to get the equation of the secant line. And I'm going to ask you to use y equals mx plus b. And what we need to do to solve this is we need m, which we have. We actually, y is always y, and x is always x when we give the final formula. We just need b. And how are we going to find b? Well, we have lots of information already. B is 6. Perfect. We have m equals negative 3. I'm just writing down this information so that we can keep track of it. We have 2 points, this and this. You wouldn't need to write this, but for those of you that need a little extra help, you can do this. Why would you use x equals 0? So, but you'd need the accompanying y value as well. So there's no real, so you would get x equals 0, y would then be negative 8, you'd put in 0 and negative 8 and solve for b. But it's actually faster not to do any calculations with that at all. I'm just going to choose from the points that I've been given, and I'm going to choose the first one, just for funsies, and put it in for x and y. So the y value is 3. The m is above -3. The x is 1, and we can solve for b. So you'll get that b is 6. So you can do whichever way you want. Abdo, you probably got 6 anyway. And so, well, if you wanted to do it your way, you would also get 6. So do it whichever way you want. I'm not going to tell you how to do it. Just whatever method you use, you had to show your work. That's all I ever ask, okay? There's 100 ways to do the same thing. I'm just trying to give you what I think is the easiest way for this particular course. But of course, there's Khan Academy, there's all sorts of ways to do the same thing. All right, what was the point? The point was to get B, okay? First step, do that. Second step would be to sub in B. So sub in M and B. -3x plus 6. And we're done now. The M was the slope. Plus 6 was our B. Hansa family ways. Whatever works. Oh, I'm sorry. I needed a stretch. Let's keep going, shall we? I'll do one more example with you, a slightly different way. We won't have the graph this time, so Abdul will be very happy about that. We'll just do it the old-fashioned way. So for this curve that we can't see, find the average slope, also known as the secant line, between x equals -2 and x equals -1. So we're going to do it the way that Abdo was probably doing it anyways. We need a point, which we need a coordinate. So we need the x and the y value. So we're going to say when x equals -2, yeah, plug in the x's. You get the idea. When x equals -2, y equals -2 cubed minus 1 over x, -2 plus 1, y equals -6. So what this gives us is the point when x is -2, y is -6. That's our coordinate that this gives us. We're going to do the exact same thing for when x equals 1. What's our y value? If you solve that, it takes very little work. It's 3 over 2. That gives us another point. When x is 1, y is 3 over 2. So we've now got 2 points. We don't need to know what the graph looks like. We make Abdurrahman very happy, and we can just go ahead and get the slope without ever having to see this pretty beautiful picture. Yeah, we get to find the slope. Slope is y2 minus y1. You don't need to write that middle step every time. I'm doing it for your benefit. 15 over 2 over 3. Yeah, you could simplify that. We'll have 3 over 2 minus -6, 1 minus -2. So again, these are coming from our y values and our x values. If you simplify that, you should get 5 over 2. Because 5 over 2 is 2.5. So you've got 5, let's see, 15 divided by 2 divided by 3 is 5 over 2. Well done. Is it okay if I don't go through the simplification of that? Because normally the slopes will be a little bit more straightforward. All right. Find the equation of the secant line. All right, same story. Y equals mx plus b is what we're dealing with here. So we know, let's just take either y value. Which one? Do we want to take this y value, or do we want to take this y value? Well, why would you ever choose to put a fraction in? Like, don't use a fraction unless you have to. So I'm just going to go ahead and use the first one. I'm going to put in our y value is -6 equals m. What's our m? Well, it's 5 over 2. Our x is -2. And then, oops, just want to keep my colors consistent here. And then we have our b. That gives us -6 equals -5 plus b. B is now -1. And we can write our final formula. Y equals mx -1. All right. Questions on that? I didn't explain it so much because we did the same thing for the previous example. I just wanted to make sure that we got through it. Yeah, I also think it's easy, but that means it's almost nothing. Because I've got a degree in math, specifically math and physics, not just general stuff. Simple process, really. You need to find 2 points and get the slope between them. And then you use y equals mx plus b to figure out what the equation is. So if that's a little bit tricky, go back, watch the video again, do what you need to do, figure it out. The rest, we can do as homework. This is basically the same. The next assignment. The assignment, as per my current schedule, is next Wednesday, a week from today. And the next test will be June 14th, which is about a week and a half on Sunday. June 10th, June 14th. You got some time. Honestly, this is the hardest part of the unit. I feel like derivatives, by the end of this unit, the derivatives are actually really simple. Once you get it, it's like, they're kind of nice to do. A lot of students like them because they're kind of just like puzzling instead of difficult. Test will be of 4 units. No, the next test will be only units 4 and 5. This unit and the previous unit. Trigonometry and derivatives. There's 2 more units after this one, but they're very, very short. And we'll just have them on the final test. All right. So let's cover tangents. And I saw that Mohammed said tangent is kind of tricky. I agree. Tangents are tricky, but we'll just do what we can to get through it and try not to hate me by the end of this class, because it's kind of the way it is. All right, it's okay, Ali. Everyone has their sleepy days. Okay, so let me set up the big picture here. What we just did was we tried to get the slope of a curved line using the secant line. The secant is an approximation. The secant obviously is not the exact slope because we are kind of cutting through the point. We're cutting off a section of the graph. The actual slope, or the exact slope, is represented by the tangent line. So when I say actual, I mean not the average slope, not like a sort of slope. I mean the exact slope. The problem is, and this is a big problem, graphically the tangent line is the slope of the curve at only 1 point. Let's just think about that for a second. When we do y equals, when we get the slope formula, we need 2 points. 1 point, 2 points. The tangent has 1 point. How can we get the slope? And the answer is we kind of can't. Not by any methods that we know so far, but if we could take the secant points, take 2 points, and get them so close to each other that they're essentially the same point, then we'll have the tangent line. Okay, so the problem is, Abdo, there's no y-intercepts, x-intercepts to talk about. Let me just show you something. This is our tangent line. Okay, let's just say this is our function. If I know you hate graphs, but too bad, it's the way it is. You'll get used to it. Look at this purple line. This is, I'll keep this up. This is the slope of this line, and the slope is actually given over here. So watch as I move this line around, it's giving me the exact slope. Okay, well thanks, Desmos. Doing my plan. This is my slope. As I move, okay, look, the slope is 1.3, so kind of nice. As I move and it gets lower and lower and lower, it gets smaller, smaller, smaller. At this point, the slope is essentially 0. It's really flat. But Desmos is doing something in the background. Desmos is doing what's called derivatives. It's getting the exact slope, but it's not using secant. It's using a special method. But you'll notice that the tangent here, there's no y-intercept or x-intercept. We don't even know what the equation of the line is. We're just looking at the graph, and we're saying, okay, wherever it touches at this one point, we need to draw a line that's perfectly perpendicular to the line at that point. Anyway, I don't want to over talk on that one because that's not really the point of this lesson right now. These are just the basic rules of tangents. You can see that that's one given tangent line. If we were to draw it at different points of the curve, it depends on x. At this x value, the tangent line is very steep. At this x value, x equals 3, the slope is actually 0. This would be positive slope. At this value, x equals 4, we have a negative slope. Okay, so I'm just trying to get you to understand that wherever we touch, yeah, so Mohammed, you're saying, should it touch with the curve? Yes, it touches, but it actually only touches once. You need to make the line perfectly so that it never crosses the curve again, okay? You won't have to graph these, by the way, for the most part. I'm just explaining this to you. So the tangent of this, if I was to try to make the tangent here, and look, I drew a line like this, that would not be the tangent line because it's touching at 2 points. I would have to take that line and do a better job. The tangent would be like that. It just touches at 1 point. All right. Anyway, I don't want to over-explain that. I don't want to make it too complicated. We just need to touch it only at 1 point. It's more of a concept, not something you need to do yourself. So it says the tangent line is much more difficult to define. It's way harder to understand than the secant, but we do talk about it when we're doing derivatives. And I'm about to blow your mind in a few seconds with probably too much talking, but I'll do my best to make it simple. First things first, it says draw a tangent line, and it says use it to calculate the slope at the required points. So it wants us, it says it down here for some reason, I don't know why, but at the points x equals 0, draw a tangent line when x is 0 and when x is 1, okay? So when x is 0, again, sorry Abdurrahman, but you're going to have to get used to this. When x is 0, we need to draw a tangent line at this point. I'm going to try to draw a line that only touches the curve once. It's going to be very difficult, actually. All right, that's my tangent line at that point. It just goes right through the curve, only touches once. It doesn't touch twice. Let's do the same thing for x equals. Do you have a question? Okay. When x is 1, we need to draw a tangent. We need to try to draw a line that only touches it once. We can't draw it like this because it wouldn't be perpendicular. We need to like just glance it. It's like an airplane coming down to the runway. You just gently touch it and you can fly off again, yeah? So like this. So it's like you're trying to come down, and you just touch it and move on again. Like you're trying to meet the curve at this tiny little point and then you move on. The problem is, what the heck is the tangent, the slope? I'm not going to get you to calculate it. I'm just going to show you that it's kind of difficult to figure out what it would be. And if you made a slightly different tangent line, you would get a totally different slope. So it's very difficult to get the slope of tangent lines. All right, I just wanted to give you an example. Same curve. different slopes at different points. It says calculate the slope of the two lines below. That could be homework. There's no need to cover that right now. We've done all that. I do want to move on to this. And this is the page that will probably haunt you for a couple days, or you can ignore it. But this is where I'm going to explain what the difference between the tangent line and the secant line are. So this is a key idea. And the big idea is that you can't usually get the slope of something until we have 2 points, right? So allow me to make you upset. Okay, what do we have here? I'm going to choose 2 points. Or I'm going to choose 1 point to begin with. Let's just say this. Let's choose a point here. I'm going to make a tangent. Why is everyone like running away? Is it a bad time? You know, the class is an hour and a half. I'm going to try to make my best tangent line. So this is my tangent. Okay, it's not the best tangent in the world. I probably could do a little bit better because I can cheat because of the tool. Okay, that's the tangent line. Does everyone agree? Thumbs up. You're all alive? Do you agree that this is the tangent line at that point that I've chosen? Yes, 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 yes. Now, the problem is, how do I get the slope? The slope is y2 minus y1 over x2 minus x1. But I don't have an x1 and an x2. I don't have a y1 and a y2. I just have 1 point. So we need to do our best guess by choosing the secant. So let me take this point. I'm going to put another point on top of that and choose another point over here maybe. And I'm going to draw a secant line, which is basically the tangent, but not quite. And it'll be an approximation. Sorry, my computer is doing that thing where it decides to stop letting me write. Okay, there we go. Computer, stop. Secant. So visually, by looking at this, even if you're not good at graphs, you should be able to see that I have one line that looks kind of like this, and I have another line which is almost the same steepness, but slightly different. So what that would mean is that the secant line and the tangent line here have similar slopes, and it's like a best guess. The secant is like an approximation of what the tangent line is. Okay, so let me show you something else here. And this is what's probably going to upset you before it makes you understand it. Let's just say we have a curve, okay? We have this curve here. We don't even need to worry about any of the extra stuff. Okay? We have this curve. It's okay, Hamza. Thanks for coming for this long. Look at this. Can we all agree that I have a curve and I have a tangent line on the curve? And hopefully you can see that the slope is about 1 point, let's just say 1.3. All right, my slope of this tangent line is 1.3. So far, so good. Visually, you can see that. I'm going to make a secant line. Oops. I'm going to draw a secant line. Right now, look at the secant line here. The slope of the secant line is not 1.3, so I can do better. I'm going to move the second point, and it'll recalculate. And the closer I move the 2 points to each other, the closer the slope will be to the actual slope. So look at that blue box. As I move the points closer and closer together, it's getting closer and closer to the answer that I want. See, the points here are so close to each other, the slopes are essentially the same now. Of course, I wanted to jump away. my point is, if we make the points close enough, the slopes will be the same. In fact, if we can make the secant points infinitely close to each other, and by that I mean make the distance between them equal to 0, or as close as we can get, they will give us the slope. It'll give us the perfect, exact slope, even though we don't have 2 points. And that's called the derivative. So let me show you, I'll clear that. Let me show you how we do this mathematically. We need a special formula for this. Let me show you how it's built. This is the point where if you don't understand, don't freak out. You're going to be able to take the final formula and use it later. But I want to try and help you understand it. This first point here, instead of calling it x1, we're going to call it x. This point here, we're going to add what's called a small distance, a tiny distance, which we'll call h. And this point is now x plus h. All right, we have 2 points, x value for one, x plus h is the x value of the other. The associated y values. What's the y value for this? It's just f of x. Whatever the x value is, it's called f of that. Let's see who's really paying attention. This is a tricky question, very tricky question actually. What is the y value for this point? Don't look at the grid. The grid means nothing. What is the general value of it? It looks like this, but slightly different. Well, it's the function when the x value is x plus h. So function when we put in x plus h. Tricky, very tricky. Many students don't understand this for as long as they do math. But it gives us an extremely important result. So I'll just write it out, okay? What's our y values here? What's y2? This is the same as y2 here. This is like y2. This is like y1. This is like x1 and x2. I don't usually like to write those in. I'll erase them after. y2, this is what builds our formula. And you can take this formula for free. I just wanted to make it for you. It's the most important formula in calculus. Okay. All right, I'm almost done. You can't hear me? Can you hear me now? Yeah, I was not talking. It's okay. If you need to go, you can go. Of course, you need to watch the video after. You're going to miss the introduction to this topic. But yeah, feel free just to go and catch up later, okay? Not everybody, just in case you have something really urgent, but I'd love it if you stayed. Okay. So let me finish my thought here. If we were able to shrink that distance between the 2 points, if we're able to shrink the distance h between the 2 points until h is 0, make it so small that it becomes 0, we would end up dividing by 0. This would be dividing by 0. We have a 0 here. We want to make the distance tiny, but that would divide by 0. I'm just going to say use limits. And I'll write one more thing, and then we'll start using it. This is our definition. You can say, what's the limit as h approaches 0 of this? This is the hardest concept in the course, and it's actually okay if you don't even understand it, but it would be exceptionally great if you do understand it, because it's fundamental. For every single bit of calculus you're going to do, so for this course, for the next course, it's important to at least have an idea of what you're doing here. But I'll give you a long story short. Okay? Long story short starts here. the limit or the slope of the tangent line is this formula. So you can use this formula. This is a formula you can use at any time. It gives us the slope of the tangent line, which in other words is called the derivative. And the derivative is the most important concept in all of calculus. This is called the delta process. Okay? So the most important piece of information, even if you totally got lost, where did everyone go? There's only 5 of you left. Do you have an assignment starting at like 5:30 or something? What's going on? The summary of this, even if you don't get the graph, I mean, the graph is important. Take time to try to understand it. But even if you don't understand it, we can take that formula here, this delta process, and use it on any function. And when we work through the math, it'll give us the slope of that function at any point. So let me show you how this works. Let's take a look at this function here, or this question. Estimate the slope of the curve. So this first question is going to say estimate the slope of the curve using secants, and then we're going to estimate the slope of the curve using tangent. All right? First things first, let's fix the numbers. Let's use x equals 1 and x equals 2. I'm going to just quickly draw those lines. At x equals 1, our tangent would look like this. If we draw the line x equals 2, so make a point at x equals 2 and connect these. This is our secant line. We can see that they're almost touching. They're almost exactly the same, but they're not identical. I can see your face, Ibrahim. Let me rewind. Pretend you're just walking into class. Okay. Hey, everybody. Let's get the slope. No, you won't. I'm just setting it up. You'll have to do some of it, but not all the sketching stuff. Yeah. I'm asking you, get the slope between the 2 points. That's what you'll have to do. You don't have to do all the other crazy stuff. Get the slope between these 2 points. So the slope between the 2 purple points here. What's the slope of the secant? It's m. It's going to be the y values subtracted and the x values subtracted. That's 3 over 1, so 3. All right, this is the slope of the secant. I don't need to write anything else there. Let me show you something, or recap something. It says estimate the slope of the curve at the point 1, 1. That's not the slope of the curve at that point, it's an estimate. So I'm going to say this is just an estimate or a guess of the slope at the point 1, 1. To be exact, if we want the exact slope, we must find the slope of the tangent line using the delta process. Also known as the derivative. Okay, so I'm going to show you how the delta process works. It might blow your mind a little bit. Okay, 1 second. You said hold up. Do they need to connect at 1, 1? No. So let me show you this. The tangent line at 1, 1 is this, that blue line, yeah? You agree with that? That's our tangent line. That's our tangent line. It only touches at one point, so we cannot get the slope right now. Well, we will, but right now we can't take 2 points and do slope the regular way. So we take 2 points that are close to it, which is what this tangent, this secant's for, and we're like, well, let's just put a secant line here, and we'll get the slope of that instead, and it'll be close, but not exact, right? That's the idea. So the idea is like, all right, the slope is probably close to 3. Maybe it's not 3, maybe it's 2, maybe it's 4, but it's at least gives us a general idea. Okay, more clear? It's smaller. Let me show you how you get the exact slope. And please, I know there's only 5 of you, but if you're going to be here, try to pay close attention. Hamid, are you even here? Or do you, I don't think I've heard from you all this whole time. Are you there? Are you alive, Hamid? Hamid Shah? Are you there? Anybody in there? Hamid? Hamid? I'll see if he texts me. Let's do the slope of the tangent at the point 1, 1. If you want the slope of the tangent, oops, use the delta process, also known as the derivative. All right, hold on to your butts. It's going to get worse before it gets better, but I promise you it will get better, okay? We need to get the slope, which is the limit as our h variable. Don't freak out. It's just a variable just like x or y or z or p or q. It's just a variable of this. We need to solve that, okay? What we're going to do is consider 2 things. What's our original function? You might not even remember what the function was, but earlier in the question, it said that the function is x squared. So I'm going to write down f of x is x squared. Because this is here, I also need that. So f of x plus h. So whenever I see my x, I'm going to replace it with x plus h now. So I just, you know, if it's f of x, you put an x in. If it's f of h, x plus, f of x plus h, that's what you replace all the x's with. And I'm going to substitute that back in my formula. But can you tell me, does this make sense so far? Do you know how I got this part? F of x plus h? I just added it in. Hey, Ahmed, nice to see you. We have the limit as h approaches 0. I'm going to substitute in these things. X plus h all squared minus x squared over h. Where did I get those from? Well, I'll delete this in a second, but this, oops, this is this, and this is this. I'm just directly substituting them. Now that we have the setup, this is all that's what all of that was about, was just to get this set up. Just do algebra. Treat the x and h like regular variables. Yeah, no. So Ibrahim, you won't ever have to like explain where it came from. I, as like a math person and a math teacher and a math educator, it would be crazy for me just to throw that definition at you. I had to at least explain it a bit, but you can steal the formula and use it. That'll make you very happy. Just take the formula and run with it. Okay? All good? Okay. So allow us to work this through. The limit as x goes to 0 of, well, I'm going to, let me simplify this or expand it. What is it? It's x plus h all squared, which is the same as x plus h multiplied by itself. So you do your regular multiplication methods. You get x squared plus xh plus xh plus x squared. So it's this. Normally I'll jump straight from here to here. So I'm going to fill that in. I'm going to put that back in. Subtract x squared over h. This didn't change. That one didn't move. Okay, I'm not trying to make this too crowded. I'm just trying to help you see what's going on here. So that was expanding the brackets. Now I'm going to cancel anything that I can. I'm going to factor everywhere that I can and try to get the limit of this thing. Just treat it as a regular limits question now. So let's see, what can I cancel? I can see a, let's see, x squared can cancel with another x squared. And that's about it. I could take a common factor of h outside. So that would be h outside of 2x plus h all over h. Now our h's can cancel. This is the same thing like we did yesterday. I'm not going to do the limit quite yet because I want you to see perfectly where it comes from. Now we can do it. Now we can get our limit. We want the limit as h approaches 0 of this function. So we just need to set the h to 0. Not the x, the h. So our answer is 2x. That's our answer. That is a heck of a lot of work to get 2x in the end. Thankfully, we're going to do some shortcuts later. The rest of the unit will be shortcuts, actually. But that is so much work to get this tiny little function. But that's what the delta process does, actually. It takes a function, it plays around with it, and it makes it smaller and easier. And then that new function is the slope function. It's called the derivative. So let me finish off this question. Okay, bye-bye, Hannah. Let me finish off this question by explaining to you what this is that we actually did. This is the derivative of the function x squared. What it does is we can put any x value into it, and it will give us the slope of that original function at any point. It's super powerful. It is the fundamental concept of calculus. So it can give us the slope of the tangent line at any x value. So what was the question asking? Does anyone even remember what we did in the beginning? If you look earlier on this page, it says, find the slope of the tangent at the point 1, 1. So I'm going to just put in the value of x. When x equals 1, slope equals 2 times 1 is 2. So our limit process allows us to get the exact slope. This is like what Muhammad, I think, who asked me about the slope earlier? Muhammad, yeah. So Our approximation said 3. It said, hey, I think the slope is 3. I'm not so sure. It's kind of a bad selection of points, but I think it's 3. And then the limit or the delta process says, hey, the exact slope is 2. And no question, that's the final answer. And the nice thing is that you could put in every single value of x you can think of. It'll give you the slope at any point. So Ibrahimi said, I'm not sure, but don't we take 1 minus and 1 plus? The reason that wait a second, which 1 minus and 1 plus are we talking about here? Because what I'm asking, just to make things clear here, it says find the slope at the point 1, 1. We just need to put in the x value 1, and it'll give us back the slope at that point. Let me make this clearer, or at least try to. Let me show you something here, because there's only a couple of you. So our curve, don't worry about most of this stuff here. Our curve is x squared, all right? My secant line, I have the point 1. Just bear with me for a second. Okay, 1, and I also have 2. Okay. I think these are 2 points here. Let me try to make this general because I don't want to confuse you. Basically, what we accomplished was, man, sorry, the surface is really struggling today. I'm really sorry. We're looking at this function. We're like, I want this. Oh my goodness, what is it doing? We want the slope at this point, you know, at the green point. So we put a secant there and we're like, all right, we'll do our best guess. What the derivative did was allow us to get the slope exactly at that point. And honestly, that function 2x, no matter what number we put in, we just change the x value now to say, okay, now the slope is negative 1 over 1.7, or the slope is 3, or move the x value around, it just pops out the slope directly. It's really, 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 really powerful. You might not understand it, but once you do, it can help. And it has a lot of consequences in engineering as well. And I'm not just saying that because I'm trying to connect ideas. Like what the slope, the derivative is related to the velocity. So if you have the position function, you get the derivative, it's the velocity function. You get another derivative, it's the acceleration. So you can talk about the motion of something, and by getting the derivative, you immediately can talk about its velocity, its speed at any point, its velocity at any point. It's super, super powerful. It's the kind of stuff that got us to the moon and got us to the space station a couple days ago. Fundamentally, it's all based on calculus. So I'm going to just do one more example because I want you to go away feeling like you're confident with this so you can see what the big ideas are. So let me finish off. I'll be done in maybe 10 minutes or less. It says, previously we used limits to find the slope of the tangent. Graphically, it's made sense. Algebraically, it's more useful to know the slope at any value of x. And the way we're going to do that is the delta process. In this case, this slope, this is the same question as before. I'm just going to put this down. Slope of the tangent is 2x. I'm just going to say, see the previous page. We did this on the previous page. It says, this is a function that gives us the slope of the tangent line at any x. So you tell me, what's the slope at when x equals 0? What's the slope when x equals 0? Zero. Okay. We don't need to do the delta process again as soon as we do the delta process once, it'll give us the slope at 0. And we can look at our graph, and it is indeed 0. What's the slope when it's 1? Well, 2 times 1. Slope is 2. So you just look at our graph, and you're like, oh, the slope up there must be 2. And I know that because the delta process. It gave us our slope function. It's super awesome. I know I'm nerding out right now, but it is. It's one of the cooler concepts in math, one of the more useful ones. At -1, we can't even see the graph, but it'll be easy. It must be a slope of -2 at that point. So it's somewhere over here, and it has a negative slope. Okay, so that wasn't the example I wanted to do. That was just an extension of the previous one. I just want to jump ahead to that one example. The derivative is found from the delta function. It's extremely important. It has a bunch of different symbols. Sorry, I just obscured some of it. This is the delta process. It's called the derivative of f with respect to x. It's called f prime of x. It's called y prime. It's called dxy. It's called f prime. It's called dy by dx. They all mean the exact same thing. They're just common notations for the derivative. And finally, the slope of the curve is the tangent line. It is the derivative. Slope is derivative. Let me do an example, because you're just going to fall asleep if I keep talking at you like this. You can watch the video if you missed some of that. I want to do just this first one, just so you can feel confident. It says, I need a deep breath now. Let's get through this. Find the function for the slope of the following functions using the definition of the derivative. That's the delta process. And let's think about the function. Before we start, I know I'm going to need f of x. Well, that one's easy. I need f of x squared minus 1. That one's a little trickier. It looks like this. You follow so far? I've done the same thing as I did last time. I'm just making a note over in the corner what the original function is and what would the function be if we put x plus h in for x. Notice instead of putting x whenever I see x, I'm going to replace it with x plus h. That's all I've done. I've just replaced it. Now I need to get the slope, which is also known as the derivative, and I'm going to use the definition of the derivative. This is when we get to use our formula. So to remind you, it's this. We're going to get the limit of this. I'm going to put in f of x plus h. This is f of x plus h. This is f of x. Have I lost you yet? Is anyone still with me? You're the dream team if you're still here. I'm really happy that you're still here. Okay, good. Easy so far. And honestly, if you got this far, you can expand it out, do the algebra, you can get the final answer. So let's do the algebra first, and then we'll get the limit at the very end. So I'll keep the limit on the outside. How do I expand this guy? Well, I'm going to have 5 outside of x squared plus 2xh plus h squared. I did that one earlier. I did the exact same thing earlier. You should be able to see it if you go back a couple pages. Minus 1 minus, well, I need to multiply through by the brackets, minus 5x squared plus 1. Hopefully we're okay so far. All over h. So I expanded my brackets and I multiplied through by my brackets. I'm trying to get everything out in a big line so that I can start simplifying. I'm going to multiply through here. Oops. Multiply through here. And I don't know why I put 3 there. I'm going to cancel these ones so I can see if they're in common and keep working through this until I get to a logical answer. 5x squared plus 10xh plus 5h squared minus 5x squared over h. Okay, what can I do now? Well, I can see on the top that I have a 5x squared and I have a minus 5x squared. I'm going to cancel those. Is there anything else? Nothing else cancels, but I can take out an h on top. I can factor out an h just like our previous question. So I'm going to factor that out. H outside of 10x is 5h all over h. And now I'm getting somewhere. Okay. It's getting smaller. I must not have made a mistake. If it's not getting smaller, if your final answer is crazy, you've done it wrong. Because if your final answer is nice and small and clean, you've done it right. That's the whole point. The derivative always makes an easier function. So this is 10x plus 5h. Now I'm going to do direct substitution. This gives me 10x plus 5 times 0, 10x. A lot of work just to get a simple 10x. But what that 10x does is if we have the function 5x squared minus 1, we can put any x value into that 10x. It'll give us the slope of that original function at any x value. So it's pretty powerful. I'll split this up. I'm not going to do this other one, unless you want me to do another one today. But how do we feel with that? Is it making a little bit of sense? Can you see that it's not as bad as it looked in the beginning? Of course, if you ever have any questions on this, you can send me questions directly. I'll go back through it. Yes, there are a lot of steps, but really you just start with the formula. Make sure you have your two functions together and then expand. But the steps, I think you'll agree, how would you mix the steps, Kevin? Actually, I'll stop now because I'm going to stop the recording. I'll still chat to you, but until next time.